Hello everyone, this is a quick video to introduce you to specific heat capacity and latent heat. Please feel free to pause the videos if you'd like to take notes and slow down and repeat bits that you didn't understand. So, there's three main things we're going to be looking at today. So the first one is we want to understand what the concept of specific heat capacity is. The second one is we're going to select and apply this equation. And then we're going to learn what is meant by latent heat of fusion, latent heat of vaporization, and we're going to learn the equation for that one too. Just so you guys know, that one has got this equation. Okay, so let's kick off. Specific heat capacity. So let's imagine that we were going to make some tea. To make tea, generally you need hot water, otherwise people are disappointed. Now, the question is, what's the quickest way to heat the water to 100 degrees? That's the temperature that we want our water. And the answer to that question is by heating just enough for a cup of tea, rather than doing a whole kettle. And then the question is why? And the answer comes down to this. The energy needed to change the temperature of something depends on three factors. The first one is its mass. So the more mass there is, the more energy you're going to need to change the temperature. So that's why if you have more water, it's going to take more energy to change its temperature. The symbol that we use for mass is m. The material that it's made of will also affect how long it takes to raise the temperature. So different materials have different amounts of heat that it takes to increase their temperature. We're going to explore this more. It's related to a factor called specific heat capacity, and the symbol that we use for that is C. The last one we're going to look at is the change in temperature that we want to achieve. If we only want to increase the temperature of something by 1 degree Celsius, you don't need much energy. If you want to increase the temperature by, let's say, 100 degrees Celsius, it takes more. So the last factor that affects the amount of heat required is the change in temperature desired. So let's look at specific heat capacity. So we have an equation for this. The amount of energy that it takes to heat something up by a certain temperature is equal to the mass in kilograms multiplied by this special constant called the specific heat capacity multiplied by the change in temperature. Note, they've given us Kelvin. Kelvin is essentially the same as degrees Celsius. You can also use degrees Celsius for this here. So the formula we're going to use is energy equals mc and then temperature change. Sometimes you'll see it written as delta T for change in temperature, and then sometimes rather than using E for energy, they use Q for heat. Either of the symbols, they're fine. Now, specific heat capacity is essentially just a property of the material. Different materials have different values for their specific heat capacity, and these are determined experimentally. So let's do a couple of examples to explore this together. So, how much heat would it take to increase 4 kilograms of iron from 22 to 50 degrees if the specific heat capacity is 400 joules per kilogram per degree Celsius? Well, the way we figure this out is the energy is equal to mass times temperature times specific heat times the temperature. So in this case, they've said the mass is 4 kilograms. The specific heat of iron is 450 joules per kilogram per degree Celsius. We're going to multiply by the change in temperature, and our change in temperature in this case is 50 minus 22 equals 28 degrees Celsius. Now note, the trick for that one there is when we do the change in temperature, that is going to be the final temperature minus the initial temperature. That's how we calculate the change in temperature. So we've changed by 28 degrees, therefore the energy delivered is going to be, so I put that in the calculator and I get 5.04 times 10 to the 4. Well, what should the units be? It's energy, so it should be in joules, but we can also just check. If we have a look at our units here, we've got joules per kilogram per degree Celsius. We're multiplying by kilograms, so that cancels that out. Multiplying by degrees Celsius, so that cancels that out. Okay, let's have a go at another example. Let's look at lead. So we have, what is the mass of lead with this specific heat capacity, 126 joules per kilogram per degree Celsius? Note, that should be per degree Celsius. That increases its temperature by 7 degrees when 3,000 joules of energy is supplied. Well, energy equals mc and then change in temperature. So in this case, we want to find the mass. So the mass is equal to the energy, which is our 3,000 joules, divided by the specific heat capacity, divided by change in temperature. So we can just substitute all this in, and we get 3.4. And the question is, what's the units? Well, they've given, we know it's a mass, so it should be in kilograms, but then we can also just check out over here. So we've got joules, cancels out with joules. We've got per degree Celsius, cancels out with degrees Celsius. Then we've got 1 divided by kilograms. So the unit's kilograms. Okay, So, question for you to consider. If you're on the beach, both the sand and the sea are heated by the sun's radiation for the same amount of time during the day. So why does the sand burn you but not the sea? The answer is specific heat capacity. Water has a very, very high specific heat capacity. It takes a lot of heat to increase the temperature of water. So the water's temperature doesn't increase that much. But sand has a low specific heat capacity. So for the same amount of energy added to it, it heats up a lot. Next, we're going to look at latent heat. And latent heat is all about changing states. So going from solid to liquid is an example of changing states. This is called melting. If you go the other way, it's called freezing. Sometimes melting is also called fusion. Alright, liquids can go to gas. This is called boiling, or sometimes evaporation. If you go the other way, it's called condensation. Now, key thing to note here is that it takes energy for these processes to occur. If you want to melt solid, you have to put heat into that solid. And that doesn't increase the temperature, that actually just starts to break up the chemical bonds. Similarly, if you want to turn a liquid into a gas, you have to break more bonds, and so that means that you have to put in more heat. So let's have a look at an example of this. This is what happens if you start with some ice and you heat it up. So the temperature over time looks like this. When it's ice and it's very cold, let's say it starts at -10 degrees, it starts to warm up. It warms up till it gets to 0 degrees. Then the temperature actually stops going up while it melts. That's because all the extra energy that we start putting in at this point here is going into breaking those chemical bonds, not into actually making the particles move faster. So when we're here at the start, the particles start moving faster when we add heat. That's increasing temperature. Here, particle speed remains the same. The kinetic energy doesn't change, but their potential energy increases until it's all a liquid. Once it's a liquid, then the extra energy then starts to increase the kinetic energy of the particles, increasing the temperature till you reach the boiling point. Once you reach the boiling point, then you need to start putting in extra energy to turn it into a gas. You're breaking up those bonds so that way the little molecules can all separate. So you're giving it even more potential energy until it becomes a gas. Then the temperature starts increasing again. So far we've been looking at what happens in this phase, and this phase over here, where the temperature increases. Now, that's when we use specific heat capacity. Now we're going to be looking at latent heat. And latent heat is the amount of heat that it takes to undergo this process and the amount of heat it takes to undergo this process. Now note, if you go the other way around, if you go from the gas to the liquid, so you're going back this way, heat is also released. It takes energy to turn a liquid into a gas, but when a gas becomes a liquid, energy is released, and so extra heat is given to the environment. That is why a steam burn is so much worse than getting a burn from hot water, because not only is it 100 degrees, but you get this extra heat coming from the fact that when the steam touches your hand, it turns into a liquid, thus depositing lots of extra energy. Specific latent heat is the energy required per kilogram to change the state of a substance without changing its temperature. So the specific latent heat of fusion is for melting. So fusion is our fancy word for melting. And then the specific latent heat of vaporization is for boiling. So that's our fancy word for boiling. And our formula for this is the energy, or sometimes you see it as the heat, is equal to the mass of whatever it is that you're trying to boil or that you're trying to melt, multiplied by capital L, where L is the specific latent heat. So the specific latent heat of fusion for water is this number here, 334 kilojoules per Kelvin, and the specific latent heat of vaporization for water is even higher, it's 2,300 kilojoules per kilogram. The specific heat of fusion for water is 334 kilojoules per kilogram, and then that's for melting. For boiling, it takes even more energy, almost 10 times as much. It's 2,300 kilojoules per kilogram. Okay, let's do some calculations together. So, how much heat is required to turn 2 kilograms of water at 100 degrees into steam? Well, at this, we don't actually need to change the temperature here, so we only have to use our formula, Q equals ml. So in this case, we have got 2 kilograms of water, and we're multiplying by, in this case, we're going into steam, so that is vaporization. So we multiply by 2300 kilojoules per kilogram. Per kilogram cancels out with kilograms, and you get 4600 kilojoules. Okay, if we want to convert 3 kilograms of ice into water at 0 degrees, we don't need to change the temperature here, so the amount of heat that it takes is simply Q equals ml, and in this case, my m is 3, and this time my L is 334. So that is 1002 kilojoules. Sorry, I've been a little bit lazy with units. Now for this last one, calculate the mass of water starting at 0 degrees that can be converted into steam using that much energy. This time we've been given our energy, but if it starts at 0 degrees, then we need to take specific heat and latent heat into account. So the total amount of energy required is the amount mc delta T, where delta T is our 100 degrees. And for that, we're going to have to know our specific heat capacity of water. Specific heat capacity of water is 4.2 joules per, kilojoules per kilogram. Okay, plus we've got the mass times the latent heat, and we know the latent heat is this number here. If we want to solve this, we need to get mass by itself. So we're going to do a factorization, C delta T plus L. So that means that M is equal to Q divided by C delta T plus L. So in this case, our Q is 100 kilojoules because it's got 3 zeros there, so that's in kilojoules. We know our L, it's 334 kilojoules per kilogram. We know our C, it's 4.2 kilojoules per kilogram. And then we've got our delta T. So in this case, we need to increase the temperature by 100 degrees. When I put that in my calculator, I get that the mass is 0.13 kilograms. Hopefully I put that in my calculator correctly. Alright, that is an introduction to specific heat and latent heat. Time for you guys to master these concepts by practicing them for yourselves.